All right, time to start. So welcome everyone to this ArbOS internal presentation and code walkthrough. We are going to start. Um, so yeah, let's start with a short introduction. So I'm Gustavo Grieco, part of the TrelloFits blockchain security team. I'm a lead security engineer. I've worked in many smart contract reviews and some blockchain reviews. And I'm going to be giving an overview of ArbOS, of the ArbOS architecture and code, focusing on the actual exploration of the code. All right. So, and if you want to follow the company's Twitter, you have the QR over there. All right. So I'm going to start with a few slides with a very brief introduction to ArbOS. So essentially, ArbOS is the core component of each Arbitrum chain. And this means that every Arbitrum chain will have its own ArbOS instance, and these instances are actually independent of each other. So they need to be initialized, and they need to be upgraded and managed individually. So each Arbitrum um, chain will have its own. So essentially, ArbOS will um, will manage the AVM execution context, and as well as calling the state transition function for for moving the blockchain from one state to another. So you can think that it will actually execute transactions. All right. And the current version of ArbOS using for this video is version 2.30. It's implemented in the Go language. And if we look back a few years ago, before the current Arbitrum technology, which is called Nitro, they used to have ArbOS as well, but implemented on a different in a different way with a different architecture and also in a different language. They used to use a language called Mini, which was specifically designed for implementing ArbOS and nothing else. All right, so right now they are using the Go programming language, uh, so we can take a better look to the code as well. All right, so let's take a very high level overview of what our voice is supposed to be doing and what are the inputs and what are the outputs. We are going to also, I'm going to describe some of the components that are not going to be detailed on this presentation. So essentially, a transaction into an Arbitrum chain starts in an L1, and users need to interact with the smart contract, with the bridge. And then the sequencer will sequence the transaction, and the messages are going to be picked up by ArbOS, by the ArbOS version that is running on the nodes, right? So we can think that ArbOS, the inputs of ArbOS as transactions. In fact, there are messages coming from the sequencer. We are going to assume that the sequencer will deliver these messages, um, but actually, ArbOS will have checks that will be similar to the ones in the sequencer and the smart contract. So even if the smart contract and the sequencer are not working as expected, ArbOS should still behave correctly. All right. So ArbOS will take these inputs, it's these messages. They will parse them. We'll see that they are valid. They will process them, and then it will use uh, some of them as transactions from the user, because not all the messages are going to be actual transactions. Um, and this means that the AVM the L2 side, the AVM side will change their state, and it will also use the ArbOS state on itself. And finally, after a number of transactions was executed, a block will be created. All right. So this is essentially ArbOS at the very high level. All right. So a little bit about the technology, and we're going to see what are the things that are going to be explained, and what are the things that are not going to be part of this code walkthrough. So ArbOS, ArbOS will be part of a node, right? And it will use directly some of the functions from the Go Ethereum as a library. There are all the functionalities from the node to be able to read events from L1. We're not going to explain that part. These basics, this stack will run in the nodes, right? Will be compiled to native code and run in the node. There is another instance in which ArbOS and the Geth, the Go Ethereum state transition will also run, which is for the fraud-proof system. But we're not going to describe that part. That will probably need dedicated videos just to explain how the fraud-proof system works. But essentially, it's going to be, that part is going to be compiled to WASM, and the WASM code will be used for proving or disproving a transaction on chain. All right, let's have a quick summary of what we are going to describe in this video. We're going to start with the ArbOS state. We're going to see what is the state, where it's stored, and how it's stored. We're going to talk a lot about ArbOS inputs. We're going to follow the path from L1 messages to L2 transactions. And the next logical step is to see how the blocks are produced with these transactions. And also, as part of this video, we're going to see retrievable ticket creation, destruction, and lifecycle in general, because they are going to be a really good example to explain the two of the hooks that are used. These are not the only hooks that are used, but two of the most important hooks that are used on ArbOS, which is the start TX hook and the end TX hook. All right, so enough about slides. Let's go to the code. All right. Okay, so the first thing wanted to introduce in this video is the use of the state. So, and we haven't talked about how ArbOS will do all the things, or how it will implement all the important features. But starting from the state is actually easier because it's very localized in the code. So I will be exploring these files, and I will be um, I will be also be detailing where these files are on the source code, so you can follow this explanation later if you want. So it's going to be easier. So we're going to start this journey in the ArbOS state um, .go file, which is in the ArbOS state directory inside the ArbOS directory in general. And you can see here the ArbOS state data structure that holds the ArbOS state. We have important things like the version, the pricing state, the state of the retrievable, uh, who are the owners of the chain, which is the chain ID, and other fields. Uh, the other function that is interesting is how an ArbOS is actually how the state is actually open. So you will different features from ArbOS needs to read and write the store, and this function will do exactly that. But there is an interesting parameter here, burner. It's going to be uh, a specific object that is going to be used to keep track of the gas use. So when a user interacts with ArbOS directly and is paying, it, it will pay for the gas, and accessing different storage areas will need to be actually measured, right? So that's why we have this. All right. So other important parts of this file, the ArbOS version, all the ArbOS instances will have versions that are independent of each other. Um, the state needs to be initialized. The chain owner, when a new Arbitrum chain is deployed, needs to initialize ArbOS with all the parameters that we described. And of course, if there is a way to if there are versions, then of course there is a way to upgrade. There are several functions to upgrade. Perhaps the most interesting one is the upgrade ArbOS version, in which you can see actual traces of past upgrades. Um, Typically, upgrades are used to improve performance, but also when there is a new version of the AVM, for instance, a new opcode, it needs to be upgraded in order to support that, because it's going to include the Go Ethereum state transition. All right. Yeah, so that's essentially the definition of the state. Let's see how the state and where the state is actually stored. So for that, we need to take a look to the storage.go file. This file will contain a lot of small functions for actually reading and writing low-level storage values like uints, bytes, and so on. So, but the first question is, where is ArbOS state stored? So, and the answer is a little bit unexpected. ArbOS will reuse the Go Ethereum implementation to store its state in an account, in a fictional account. You can see the actual address of the fictional account. This account will not be able to execute anything, will not have code. But regardless of that, the state will be used for actually keeping track of all the uh, all the data structure that we just described. All right. So yeah, this is the file. But so perhaps you were wondering why this is the case. So there are two important reasons for that. The first one is the developers avoid needing to create another type of storage or create a new database that needs to be saved and restored. But perhaps the most important reason is like uh, the storage. If ArbOS reuse the an account storage, it will automatically handle things like reverts. And in that case, typically what will happen is uh, there is a smart contract that interacts with ArbOS, and then we'll do other transactions. If the transactions revert after interacting with ArbOS, all the all the state of ArbOS needs to be reverted. All right. So if the storage if the storage is saved in an account, this will happen as part of the Go Ethereum API. All right, so that's a quick overview of what is the store, what is the state of ArbOS, where is the store, and how. But the important part is what ArbOS is actually doing uh, as well. So in order to explain that, we're going to start uh, with with the inputs of ArbOS. So um, so ArbOS needs to change the state of the blockchain. So all the inputs should be properly defined. It should have no interactions with external files. It cannot have interactions with the network. It should the outputs of ArbOS should only depend on the actual inputs that needs to be coming strictly from a1, right? So, and as I explained, we're not going to describe it in neither the bridge in the smart contract nor the sequencer. Instead, we're going to start our review in the inbox file where the nodes will start parsing data that is coming from the sequencer, and you will uh, you will be able to see data in raw form as list of bytes. This data will be parsed even if the validation was already performed in the actual smart contract, right? So you can see here different stages of this initial parsing. Messages, raw messages are going to be parsed into a data structure called L1 incoming message, and also the data from the actual sequencer can be compressed. So it's going to be decompressed using broadly, and all the valid segments are going to be parsed into L1 incoming messages. So yeah, it's also um, yeah. So, but we need to explore a bit what are incoming messages, right? So you can see on the incoming message.go in the ArbOS types folder, you can see what is an actual L1 um, incoming message. It's going to have a header, and the most important part is the kind. So we will have different kind of messages, and here you can start to see typical operations the that the users will perform. right? So things like a deposit, submit retrievable, actually sending transactions. These are going to be L1 messages at the beginning of the parsing procedure. And so these functions will uh, validate the header and then um, parse the actual L1 message, but as a simple list of bytes. They're not going to be deeply parsed because if there is an issue with the headers, these are going to be discarded, right? And we are going to see how how the use of these incoming messages are going to influence how how the system works, or it's going to enforce a property about the system. All right. There are also a special type of message, which is the init message. This one will only happen once in the lifetime of a chain. It's going to be at the initialization, and there is a specific function here in incoming message in order to parse it. All right. So we just review how how data is actually coming from the sequencer. We're going to see um, when this data is actually validated with all the fields. For instance, a deposit or a retrievable ticket. That will happen on the next step. And the next step will be to take a single, to take each incoming message as individually and parse L2 transactions. So each L1 incoming message will be parsed into 0, 1, or more L2 transactions. Right, and this is going to happen on the parse L2.go file, mostly on the parse L2 transactions function and on the all the dependencies. And here you can see parsing of some important type of messages. Um, for instance, a deposit, a simple deposit, will be parsed into a single transaction. Um, there are other messages that are going to be either invalid, so it's going to parse into zero transaction. Some of them will be parsed in two. For instance, the L2 funded by the L2 funded by L1, it's a deposit and then a transaction. So users can fund an actual transaction and then execute it. So these are the basic types. However, there is one type of L1 message that will contain an L2 message inside. So you should not confuse an L2 message with an L2 transaction. So an L2 message is a message that goes inside an L1 message, and it's going to be parsed eventually into a number of L2 transactions. So we're going to see this function, parse L2 message, which is here. You can see different types of L2 messages. For instance, a contract EX, an unsigned, either an unsigned transaction or a signed transaction, and a batch. This this um, this L2 message is actually interesting. So a batch will contain a list of L2 transactions, and this can be recursively used up to some limits, right? So you can see parsing of batch transactions, L2 messages, it's here, and it's going to return a flattened list of these messages. as transactions, right? All right, so we have the basics on parsing L2 transactions. You can see in this file a little bit, for instance, how all the deposits are parsed. And they are going to be um, a specific function will be created, a specific type of transaction will be created to execute the deposit. All right, this is not going to be a normal execution of a smart contract. It's only going to provide balance to certain accounts. All right. And there are other functions like parse, submit, retrievable. We're going to come back to the retrievable tickets later, so we're going to see this in detail. All right, so these are typical L2 transactions. We are going to see how these are going to be used, because this is going to be an important property of the system. And for that, we need to go into the block production, the actual interesting part of the system where the transactions are going to be executed. Right. So there is this file blockprocess.go. We can see here the produce block function. This function it's going to take a single L1 incoming message and will produce a number of L2 transactions. And this is going to give us already a property of the system. In ArbOS, every L1 incoming message, it's guaranteed to live in their own block, even if it parses as zero message, as zero transactions. We are going to see that when a block is created, there will be at least one transaction executed. But this is not going to be a user transaction. It's not going to show in the actual block explorer. It's going to be something internal. But at least one transaction will be processed. So and this function already give us an idea of some of the things that can or cannot happen. So, for instance, if there is an upgrade of ArbOS, the upgrade will be on a single L1 incoming message, and there will be no other user messages, right, to process. That means that an upgrade will happen on a block and nothing else, and following blocks will have the ArbOS version already upgraded. So this already gave us some important properties of the system. All right, so but let's take a look on how these transactions are actually executed. And this is going to be on the produce block advance, which is the function that do all the heavy lifting. So as I mentioned, it will receive this list of transactions that can be empty, but actually will append a special transaction that is an internal TX star block, it's called. So this list will have at least one element. However, this will not be a transaction that will be executed. It will be a special internal one. And we can see here that it saves all the important information about the block. And it's guaranteed to be executed first, right? It will have the chain ID, the gas, the block number, and other fields. So after we have our list of transactions, we need to iterate over them and start with the execution, right? So that's why we have this loop over here. And you can see the loop that takes at this condition on the number of transactions that are on the queue, but also on the list of redeems. We're going to take a look to this a little later when we talk about retrievable tickets. But so far, we're going to ignore the branch of the redeem, so it's going to be easier to understand how transactions are usually parsed. So we're going to ignore this. We're going to go directly into the case in which there are no redeems and a transaction will be executed. So the idea is it will take the first transaction, remove from the queue, and then we'll actually create some functions to do the execution of the actual transaction. This will typically means that it will check the validity of the transaction on itself, which checks like intrinsic gas, the nonce, and other things. So this will happen here, as you can see. And then there is the actual execution of the transaction with all the state change on the AVM. That will happen not on the ArbOS code itself, but in a call to the Go Ethereum code, and it's specifically on the apply transaction with result filter, and it's going to do all the steps that Go Ethereum has for the actual execution, like reading all the opcodes and execute them one by one, checking the gas, and so on and so on. All right. So it will execute potentially, and then will return um, a receipt that will be used later. And that essentially will put the a transaction into a block. All right, and it will do some other bookkeeping around the balances, around the use of the gas. We would check that the gas of the block does not actually exceed, and other things. However, there are some important details here that are going to be they are hidden from the user, from a developer reading this code, and these are hooks. These are the actual start TX hook and the end TX hook. You won't be able to see the hooks on the ArbOS code because the hooks are called inside the Go Ethereum code. So inside this function, there will be other internal functions that will eventually call the hooks, right? But in order to do this, in order to explore how these hooks are actually what they're actually doing, we're going to go into retrievable tickets. So that's why I have this short summary of retrievable tickets in case that you need to remember. So retrievable tickets are a feature that the Arbitrum chains implement, in which user can submit transactions that can be re-executed if they fail. If they fail for a number of reasons. If they fail for the lack of gas, and if they fail because they revert, they can be re-executed. They can be redeemed, what is called. And the idea is we have the creation of the retrievable ticket that starts in L1. We're not going to go into that part, but we're going to go into the how ArbOS process this. After the ticket is created, ArbOS will try to automatically execute the transaction. Will not need the user to do a manual redemption, but instead we'll try to execute. If it executes correctly, the ticket is removed and that's the end of it. If it's not, it will go into the delay execution queue and needs to be manually redeemed um, up to the point that it's executed correctly, or it's either canceled or the time of the ticket is expired. Users can also extend the expiration time um, if they pay like an extra fee for that. All right, so let's take a look of retrievable tickets, starting from what is the actual um, state. So you can see the retrievable.go file in the retrivables directory, and this contains some basic data structure for the retrievals. The retrievals will have an ID, and will have all the information needed for the actual execution. Right, is going to be provided by the user. They are going to have a timeout as well, because they're not going to be on save forever. They're going to stay for by the default a week, and they can be extended if necessary. So how the tickets can be created? Well, there is the function to create retrievable, which is quite straightforward. It's going to actually set up all the values, and that's it. Um, and after they are created, they will be saved, and when when they are needed, they're going to be open. And this means that they need to check for validity, because in some cases the retrievable could be already redeemed or canceled, right? So in that case, tickets needs to be checked for that, or it could be a case that it expired, right? So of course, at some point it will be removed in the delete retrievable. Um, so it's going to clean the storage. Um, And there are a couple of other important functions. As I said, the tickets can be, the expiration of the ticket can be extended, paying a fee. We're going to check this at the end of the call if we have time. Um, and finally, so as I mentioned, ticket will be eventually removed, but the way in which they are removed are not um, are not so straightforward, in the sense of retrievable tickets will need to um, they will need to expire first, but once they are expired, they're not immediately removed. They are going to be they're going they're going to be sorted in a queue, uh, and every time a user calls one of these functions to create a new retrievable or interacts with ArbOS, this function will be called, and it will take the oldest ticket, and if the oldest ticket is expired, it will remove, but it will not remove the following ones if they are expired. The reason for that is to avoid the denial of service, in which tickets an attacker fill up with a lot of retrievable tickets, and an unlucky user call this function, and all the tickets are removed one after the other in a loop. Because remember that when a user calls ArbOS, he will need to pay for the gas. So we don't want users to be paying for the execution of a loop, right? So that's why it's going to be the removal of tickets is going to be amortized over all the calls to the actual execution. All right. And then once the tickets are ready for the execution, they need to be executed in a specific transaction, which is going to be Arbitrum retry TX. So this transaction transaction is going to be actually executed, because the creation of the ticket will not execute any AVM changes. It will only execute perform changes on the ArbOS state, not in the actual AVM state. right? So that's why there is a difference between the submission and the actual execution. These are two different uh, um, uh, transactions, actually. All right, so that's an overview of the basic retrievable tickets, but how is this implemented exactly? So um, let's take a look to what happens when there is a retrievable ticket that is going to be parsed. So we are going to go to parcel to transaction, and you can see that the parsing of the retrievables, it's here in this function, which is a little bit down. Yes, here. So it will parse all the fields, and it will create a transaction called submit retrievable tx, which should not be confused with the actual Arbitrum retrievable tx. That is going to be the execution of what the user wants, and this is the creation, right? So the first thing, it will create a transaction that is going to be the creation of a retrievable. We're going to see how this will actually change the state, right? And in order to do that, we need to go back to the block creation, right? So we're going to start from the beginning of the function, from the process block advance. It's going to imagine that the user submits a retrievable ticket, and it's a transaction that is going to be in the list, right? And it's going to be executed. Um, it's going to be executed on the here, right? But since it's not actually carrying any execution of the AVM code, it will only change the state of ArbOS. And in order to do that, it's going to use the hooks. Hooks are defined in the TX processor file. So here, it's the txprocessor.go. And we are going to take a look to the start hook, which is going to execute before the transaction is actually executed. And let's pay attention to this return value, ntx now. This return value will um, signal the rest of the code that there is no need to keep executing this transaction. All the changes that are needed, all the execution, let's say, that is needed for this, it's already performed. So there's no need to go into the following steps. We can just end the execution and then process the next transaction. So we are going to see that in the start TX hook, we're going to see things like dealing with deposits. They're going to be at the beginning of the transaction. But also we're going to see submit retrievable. And this is going to check all the information about the retrievable to see that it's valid, to see that the user pays enough for the gas, and all this. If there is an issue on the amount of gas that the user pays, because it could be the case that a user pays for an amount of gas and then there is a spike in the gas that affects L2. So the gas that they pay when it's submitted is no longer valid, and it increased, so it cannot be executed. Then ArbOS will send immediately the ticket to the delay execution queue, right? It needs to be redeemed manually. But assuming it's not the case, what will happen is um, the actual retrievable will be created first, and it will be if the gas is correct and all the data is correct, it's going to create the actual transaction to execute. It's going to create the actual transaction that will carry all the user provided data for the execution of the transaction of the retrievable, right? And it's going to trigger a redeem. So it's going to do the auto redemption, right? So this is going to um, take all the information from the redemption and signal the block processing code that there is a redemption that is needed, right? And the other thing that we'll do, it will return true on this parameter that I was telling. So there's no need to continue executing this particular transaction because the ticket was already created. And there is a redemption in the queue that will create another transaction to be executed, right? But we will take a look to that. So, all right. So at this point, the execution of the Arbitrum make retrievable TX, it's finished. So there's no need to continue. We're going to go back to the block processor. It's going to iterate. It's going to loop. It's going to come back to the beginning of the loop over here, and it's going to. But before, at the very end of this loop, there is it will check of the redemptions that all the transactions created. It will be a new redemption. So we're going to see on the beginning of the loop that it's going to check that the redemption queue it has an element, so it's going to take this element as the new transaction. So the redemption will be the redemption information will be used as the transaction to be actually executed, right? And this will cast the actual transaction as the Arbitrum retry TX, right? Again, this is not the creation of the ticket. This is the actual execution of the ticket, and the system will continue. The block creation will continue with this block with this transaction, right? So how is this handled? Well, we're going to go back to the TX processor, and it's going to set up on the actual start TX hook. It's going to be this type retrievable transaction, and it's going to set up all the information for the actual execution. For instance, you will put the value that the user wanted, that is saved in the meantime between the creation and the execution. And now this is ready for the actual AVM execution, because this will return false. It means that there are additional steps to continue on this transaction, and it will execute as we expect. And then there is the last part, which is a really important one, which the block production will check if the retrievable actually if the transaction of the retrievable actually executed correctly or not. And that will happen on the end TX hook, right here in the end TX hook. We're going to check for underlying type equal to retry TX type, and that is the actual execution of the retrievable. And this hook will take not only the gas that is left, but also if the actual execution, if the actual transaction reverted or not. So it's going to be the success boolean, and it's going to do some bookkeeping, and it's going to check for the success. If the ticket was executed correctly, then the return will be removed because there's no need to execute it again. If the retrievable failed to be executed, it will not remove the ticket. But it will move the value of the ticket. So in order to do redemption of the ticket, a user needs to provide gas again. But the call value will not need to be provided again. The call value is part of the value that is submitted for the actual retrievable. So the call value should be properly saved in an escrow address for so it's going to be ready for the next execution, right? So yeah, basically um, this will execute the retrievable. We'll check if the retrievable was correctly executed or not, and then other transactions can be processed in the block. There is also manual redemptions. Manual redemptions are going to be performed directly calling a specific precompiled contract, the arb retrievable TX. This is located in the precompiles directory in the arb retrievable, and it's going to need, so the caller needs to provide the CAS. It will open the retrievable, will check that the retrievable is not expired, and then it will actually put the transaction in the queue, add a redemption into the queue, right? So in the same block will be executed. But actually, the caller will not see if the ticket executed correctly or not, because that's part of another transaction. So it will immediately return to the caller. The caller will not have any feedback if it executed correctly or not. But on the same, it is guaranteed that in the same block it will be executed. So other important operations that the users can do, they can keep the ticket alive, paying for an actual fee. So it can be extended up to a certain point. And it can also be canceled. So a ticket that is no longer needed can be canceled, and by only the beneficiary, and um, and they can reclaim at least part of the fee that is used. So they are actually going to get back part of the value that is used on the retrievable tickets. All right, so that was a lot, I know. So if we come back to the actual slides, um, we did we 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 took an overview, basic overview of some of the core components, some of the core functions of ArbOS, state, inbox, outputs, block production at some high level as well, retrievable tickets with some detail, and we cover the start TX and the NTX hook. So I will check for questions. So if you have questions, please type them on the chat. Let me see. All right. If there are no questions, this is the end of the video. I hope that you enjoyed.